Hi everyone, welcome to Python tutorials, where we've been talking about deep learning for the last few videos. And in fact, in the last dozen videos or so, we've been trying to focus on understanding various terminology that goes into deep learning. So hopefully most of you feel comfortable with the terminology. And in fact, in the last video, we looked at the various types or categories into which a machine learning challenge can fall into, including regression and classification. So in this video, let's focus a bit more on regression, and let's also look at Python code for a specific example. But before jumping into our Google Colab, let's quickly remind ourselves what we talked about when it comes to regression. Well, regression is predicting a continuous outcome. This is not just class A or class B. Instead, this is where we are trying to predict an outcome that's continuous, and this can be literally infinity, right? Infinite choices. It's not like you have a handful of choices. And the outcome is typically a numerical value, and of course, there can be many variables that are resulting in this outcome. So, for example, you have let's say age and location and square footage of a house, and your outcome is the price of the house, right? There are many variables that defines what the price of the house is. That's a classic example of regression. And there are many algorithms that you can use to fit a model for regression. And we have already looked at linear regression in the past. We looked at support vector machines and logistic regression, and also random forest, but mostly for classification, but can also be used for regression. And in this video, we are focusing on deep learning or artificial neural networks. And in this case, the deep learning will probably use just a couple of hidden layers, not too deep, but still falls into the category of deep learning. And while we are doing that, let's also fit a random forest on linear regression model and compare all of these. And the example we're going to work with is the house prices dataset. And again, let's jump into Colab so we can go through the description of the data and also how we approach fitting a model for using deep learning. So let's jump into our Colab. So as usual, I'm going to share the code with you, so please focus on the video for now. The dataset can be downloaded from this link. I'm going to leave the link as part of description. And just a quick note, the data has white spaces and not commas. And why is it important? Well, when you use Pandas to import this file, you have to mention that it has white spaces. Otherwise, it's not going to get the formatting correct. Okay, that's just a side note. Now, this data reflects house prices from 1978. So don't think that house prices in Boston are only $50,000 or something. This is back from 1970s. Okay, and this data set has 14 columns. If you arrange this into columns and various rows, and each column is a different attribute, and the last column called MEDV, it's a median value of median price of this house. And this is exactly what we are trying to predict. So in summary, we have 13 attributes that lead towards a median value, which is the attribute that which is the outcome that we are trying to predict. In other words, our X values are all the way from 1 to 13 here, and our Y is this median value. And some of these attributes, for example, the first one, per capita crime rate by town. Of course, it defines what the median value of the price is, right? So that's pretty intuitive. And there are a few others that I'm not familiar with, like nitric oxide concentration. I'm not sure why that is a thing, but anyway, that's something that we have. And average number of rooms per dwelling, of course, again, it defines the price value. And what else is there? There seems to be the proportion of blacks by town. This is very offensive. I don't know why this is this. I mean, of course, it's useful attribute to see if that has an effect, but unfortunately, we live in a world where that is an attribute that defines the price of the house. So, okay, moving on to the code. So let's go ahead and import all the libraries that we need. I'm importing some libraries that I may not be using, like Keras Regressor, because I plan on actually using random forest, to compare. So, but I'm just importing these. Anyway, so let's go ahead and import the standard libraries, and then now let's go ahead and use our pandas to read the CSV file. I've already connected this to my Google Drive right there, so and copied the link to this CSV file. And please note that we are saying our delimited white space equals to true, because then it separates it based on the white space. Otherwise, again, like I said, it won't be formatted the right way. So let's go ahead and run this. And other note I actually gave here is, did I mention that here? It comes with no titles. It doesn't come with the column names actually. So if you look at the data, I'm printing the top 5 rows here. You see the rows are given values 0, 1, 2, 3, 4, and so on. So the data is just a bunch of numbers with white spaces. So we need to format a bit. So let's go ahead and first provide the column names, because we already know the column names. It's given as part of the description of the data set. So let's go ahead and give the column names. I was doing something ridiculous here. So let me change this to price. Instead of MEDV, I don't like that because it doesn't tell me exactly what that is. I had to look up a couple of times to see what that actually means. It's median value, right? So here I was actually labeling it as MEDV and then changing the column name to price. So I shouldn't, I mean, no point in doing that. So let's comment that part out, okay? So now let's go ahead and define our feature names, or the column names, feature names. And this is a list of all of these column names. And now I'm just saying df.columns equal to my feature name. So in a way, I'm just assigning my column names. So let's go ahead and print that. So you can see that our column names are now appropriately labeled. You can print describe your data frame. So it gives us a good idea of what the mean values are for all of these attributes, right? And I'm transposing this because otherwise these will be column names, and it will be cut off, and you won't see them in its you won't see all of these values. Now you can clearly see that some of these are like in less than 10, some of these are about 10s, and this is 100th, 68, 400, 356. So the values range pretty broadly, so we have to scale them. Okay, so that's one quick note from here. Now let's get a bit more understanding about our data. So I'm plotting price, age, and tax. And by the way, this age is not the age of someone who is buying the house. This is actually the age proportion of owner occupied units built prior to 1940. Okay, what percentage of these houses are occupied by owners of the houses that are built prior to 1940? Okay, this is not. This has nothing to do with the age of the purchaser of the house. Okay. Anyway, so you have all of these values, and now we are plotting them just to get a quick idea of how the distribution is. Again, if that's not, and if you want to look at the data further, you can also do some line plots like I'm doing here. Again, I'm doing this just to get a good idea in terms of, is any of these like affecting the final price? Like, is there a linear relationship? Of course, they have an influence on the price, but is it linear? I'm just curious in terms of the relationship, but I don't know. I mean, it's unclear, which is good. Now that's why we have machine learning, right? I mean, where you can fit non-linear relations. If it's just linear, just use linear regression and you're all done. Okay, now another tool, we have used this again in the last video to understand the data. I always look at the correlation between all the attributes just to get an idea, are there any one that are highly correlated? And if so, why are they highly correlated? In the last video, we saw that our radius and perimeter and area are highly correlated. Obviously, they're correlated because they're related to each other. But here, they're not correlated much. I mean, the only two things that are correlated are a little bit above 90% are tax and RAD. I don't even know what they are. Tax is full value property tax, and RAD is accessibility to highways. So apparently the tax is somewhat related to how accessible they are to highways. Again, this is again mid-70s, so maybe it's a good thing for them to be near a highway. But now we tend to live more in the suburbs, far away from highways, so it's not noisy anymore. Okay, now let's move down to the next step. again, we're following our 7 rules that we talked about in the last, or 7 guidelines, I should say, we talked about in the last video. Understand the data, clean up the data, pre-process it, and then get to the model, right? So we are following pretty much that intuition. Okay, so none of my data points are empty, so I'm good to go. Next step, we have to define our X and Y. What is our X? All the columns except for the outcome, which is price in our case. And our Y is exactly the price column. So that's what we have here, defining those. And then we are separating X train, X test, and I'm putting about 20% of my data into the test size. So let's run this. So far, nothing surprising, right? I mean, this is all the stuff that we learned in the past 10 to 15 videos. Okay, so we know that our X values range from 0.00 something to 400 to 500. So we have to scale them. Go ahead and experiment with min-max scaler. Here I'm using standard scaler. If you don't know what I'm talking about, you probably haven't watched the video about scaling and normalization. I definitely recommend you watch that first. So let's go ahead and fit this or scale the values so the values are all within the same range, so they're all comparable. So when we fit the model, it's not giving preferential treatment to high values, and not including the low values. In fact, in a way, we are helping our gradient descent to converge faster by doing these pre-processing steps. Okay, now what type of model do we want? This is structured data. There are no images here, so we don't need any convolutional layers. We only need the dense layers. So we are going to use sequential method. And let's go ahead and use 2 dense layers and then the final output layer. So the first one, 128 neurons, and our input dimension is 13 because we have 13 features. And the next one is 64. And again, in both cases, our activation function is ReLU. Again, please watch my video on activation. We established the fact that ReLU is a great activation for hidden layers, and for the output layer, the activation depends upon the problem. So for regression, that can be linear activation, and for prediction like classification, it can be sigmoid for binary, and so on. So let's go ahead and use linear for the output layer here. And again, we are outputting only one value, right? This is a regression with one output. That's it. If this is multi-class classification, where you have 10 different classes, this value would be 10 because it's one of the 10 values. That's the correct answer. But here it's just a regression. So our output is just 1. Now, we need to compile the model. What loss function are we going to use? Again, this is a regression problem, so mean squared error is a great loss function. Again, in linear regression, this is exactly what we are trying to minimize to fit a linear model. So if you only have like this one layer, that's it, then this is very much equivalent to a linear regression problem. And for optimizer, let's use Adam. This is based on stochastic gradient descent. Again, we talked about optimizers in our previous videos. Please go ahead and watch it. So what metrics are we going to track as the epochs go by? Let's do mean absolute error. You can do mean squared error. Let's just look at mean absolute error. And that's it. Let's go ahead and compile the model and see how well it does. I don't know if this is the best model for this. Okay, in fact, maybe we should just do like 4 or 5 different models and fit the data and look at the ROC curves, right? In the past video, in the last couple of, not the last one, the one before that, I believe we talked about ROC curves, where if you get a perfect classifier, where it classifies everything perfectly, then you get like a perfect ROC curve, which is a vertical line and a horizontal. Okay, again, please watch that video. So obviously I'm struggling to explain it or making it visual for you guys. So there are 10,000 parameters that it will be training as part of this training process, and let's go ahead and fit it. And we are fitting it with these values. In fact, X train scaled Y train, and I'm separating validation split as 0.2. I shouldn't have done that. In fact, I should have given validation data. So if I do this, does it actually prompt? You see validation underscore data. So here, let's actually remove validation split. Validation split is if you haven't already split your data into testing and training, right? So which we have already done. So I'm not sure why I did that, but let's go ahead and give validation data as, sorry about this. I should have been a bit more prepared, but this is fine. X test scaled, right? X test scaled is our X and our Y is just Y test. Okay, so this is our Y. So you can give validation split or you can give validation data. Because we have already done the split beforehand, let's just give this validation data. Okay, that's the only difference. And let's run this for 100 epochs. It should be pretty fast. We are on GPU, so let's go ahead and run this. And as you can see, this is very fast. And as it's training, it's giving us the, sorry, let me go back to the top of this. It's giving us the validation loss and validation mean absolute error, and the loss should go down. And in this case, because we're looking at error, the error also should go down, right? So I think it's doing a good job overall. So everything is going down right there. So the only way we know if it has done a great job is if we plot these two, the loss and the error. And let's, oh, that it converged pretty fast right there. You see how the loss went down, and this is validation. So again, if you watched my videos in terms of dropout, for example, and normalization, so these all affect, or influence how this model looks like. So if you look at this, it says here the red line indicates the validation data, and validation is getting worse and the training is getting better, or validation is staying put and training is getting better. That tells me the model is overfitting a little bit right there. Not pretty bad, but overfitting a little bit. If that concerns you, you can always go back. Sorry. That concerns you, you can always go back and add a, probably the reason is we do not have a dropout layer here. So you can go ahead and add dropout. Did we import that? I don't want to. No, that's, I mean, I hope you got an idea there. I'll let you experiment with that. Just after this, put 20% dropout, and after this, put 20% dropout, and you will see a very nice change right here in terms of both of these going in the right direction and minimizing the separation. Okay, again, please watch my video on dropout. Okay, this is acceptable to me. Let's go ahead and make the predictions, predict on the test data itself. Okay, so what is our test data, which is our X test scale, right? So let's just look at these and make a prediction. I'm just looking at the first 5 and then making a prediction. So the predicted values are 20, 20.19, 19, 21, and 12. And here the output, the real values are 21.2. Well, we got 20. This one is 20.6. We got 20.2. This one is 21.5. We got 19.3. 21.7, we got 21.6, 13.4, we got 12.78. That's not bad, actually. That's pretty close by. In fact, I'm almost tempted to add the dropout layer and make this a bit better. But again, I want to leave that exercise to you because you know how to do it. We have covered that even in the last video. We had a model with dropout. Okay, that's good. But now let's compare this with other models. Let's compare that with linear regression and random forest and see how keeping in mind that we can actually make this even better by adding the dropouts and others, by engineering our model. Okay, so first of all, to compare that, let's go ahead and print out 2 metrics, which is one is mean squared error, the other one is mean absolute error from this model, right? We called it model, so these are the 2 values. 12.62 is the mean squared error, mean absolute error is 2.6. Let's compare how others actually perform against this. So for that, let's start with linear regression. So from scikit-learn, I'm importing linear model. And also from scikit-learn.tree, I'm importing decision tree regressor. I don't think I'm using decision tree. In fact, I'm using random forest regressor down here. Again, these are something that got left over when I was doing my experimentation. So let's just focus on linear model. We are using linear regression. very easy to use, right? I mean, we covered this in the past. You just use your X and Y values and you're just predicting it. And then we are calculating the mean squared error, mean absolute error, just like we did up here. So this should be pretty quick also. There you go. So with our linear model, we got higher error, like 16.5 and 3.05. So we already know that deep learning in this case is doing much better job. Okay, so that's one note now, notification. And random forest probably does a very good job, because random forest is usually very good at these type of problems. So let's see what what we get here. So from scikit-learn ensemble, we are getting random forest regressor. In the past, we used random forest classifier quite a bit. So we're using regressor. Let's use number of estimators as 30 and just model.fit. Again, we have done this quite a few times in the past. And then we are predicting and we are calculating error, both mean squared and mean absolute error. And we are just, in addition to printing those, I'm also printing because with random forest, you can actually print out feature rankings. I'm curious what features actually random forest found important in making these predictions. So let's print all of this out, and this should also be almost instantaneous. First of all, look at mean squared error, 12.25, 2.38. Slightly better than our deep learning, actually. Slightly, but again, if we tweak our deep learning a little bit, we may get better values. And which ones actually had highest influence? These two. Whatever LSTAT is and RM. You see 47% and 33%. All the other ones contributed, but not as much. LSTAT and RM. Now I'm a bit curious, so let's go back and check LSTAT and RM. LSTAT means percent lower status of population. Yeah, apparently, I guess if you have the same area or same house in slums, or if you have the same thing where rich people live, of course the value of the price, the value of the house is going to be different. So LSTAT makes sense. And the other one is RM, average number of rooms per dwelling. Yeah, these two are no-brainers. Of course it makes sense. Now, just because of this one single fact, you see how random forest can report the feature importances, and immediately we realized, oh, this is why the house prices are different. This is how these attributes affect the house prices. This is exactly why I love random forest or gradient boosting, where you can report these type of feature rankings. Unfortunately, with deep learning, it's still a little bit of a black box, so you don't know exactly what factors made what type of influence. You can look at the weights and you can kind of infer something, but again, it's not as clear as what you have here. Okay, so you see now how regression problems can be easily tackled by using deep learning or artificial neural networks. So I hope you really go through this exercise of adding some dropout layers in between, and also maybe dropping one of these layers and only using like dense 64. Maybe a simpler model will give you better result. I really want you to test those things out, because this can be very, very educational. So thanks again for watching this video. Again, in the next video, let's look at binary classification and how we can read a bunch of images and then classify them into malarial, infected, or uninfected. So please subscribe to this channel so you're notified when that video gets uploaded. Thank you.